All right, so last two sections here. And the first we're going to talk about, 10.6, has to deal with segment lengths. In the last segment, or sorry, the last section, we dealt with all the different angle types that could come about in a circle depending on what pieces we're creating them, tangents, secants, chords, all that kind of stuff. Now we're going to shift our focus and talk about finding different segment lengths in a circle, depending again on what creates the segments, right? What type of segments we're looking at. Some definitions here that we don't need to get too caught up with. Two chords intersect in the interior of a circle. Each chord is divided into two segments that are called segments of a chord. I think that makes a ton of sense, but it's there. The theorems are the one I'm mostly concerned about. So this first theorem says that if two chords intersect, then if you multiply their pieces together, then they're going to be equal. Now the thing with this theorem is you have to be careful that you're not mixing and matching. We have to multiply down each chord, right? We're going to multiply the pieces of each chord together. So what I mean is we're going to take AM times MB, right? So the pieces of the same chord we're going to multiply together. And they're going to be equal to, here, ZM times MY. So we're going to go down the same chord, just multiplying the pieces together. And if you reference your spinner right now on the segment side, on the outside of the white circle it says, where do the segments intersect? Where do they cross? They cross inside or outside, and these guys are crossing inside. And so if you go to the cross inside pi piece, you'll see it say, take piece times piece and set it equal to piece times piece. Okay? And that's what it means, right? And just multiply the pieces of the same chord together. For example, here's one. So you're looking at this, we're definitely dealing with segment lengths because they're right in the middle of these segments, right? There's not a degree symbol on them, so we're not talking about degrees. There are no angles or arcs given in the picture. So we're on the segment side, we ask, where do they cross, inside or outside? And they cross inside. So we're going to want to do piece times piece equals piece times piece. So we're going to take x times 4 and set it equal to 8 times 6. Divide both sides by 4, and x is 12. And that's it. That's all there is to it. Okay? Next theorem, after this definition, again, and I think it makes a ton of sense and whatever, but it's here. So a secant segment is, secants are lines. If you cut that secant down into a segment to where one endpoint is outside the circle, then it's still considered a secant. It's called a secant segment. And then there's an outside piece that we're going to call the external segment, or the outside piece, really. So anyway, a couple definitions. Theorem. Okay, this guy says if two secant segments cross outside, they're going to cross outside, then basically the relationship that exists is that we're going to take the outside piece times the whole thing and set it equal to the outside piece times the whole thing. That's what ends up being equal to each other. That's what you see over here. PS is the outside piece, PT is the whole thing. PQ is the outside piece, PR is the whole thing. Okay? And if, again, you go to your spinner, it says where do the segments cross? They cross outside, so you find cross outside window, the pi piece there, and you're going to want to match up the picture. Okay? And so make sure you're looking at two secants, and it'll tell you, right? Take the outside piece, take the outside piece times the whole thing, and set it equal to the outside piece times the whole thing. Okay? So let's try it. Here, we've got two segments crossing outside. And so cross outside says take the outside piece, which is 7, times the whole thing, and you got to be careful, the whole thing is 13, and set it equal to the outside piece times the whole thing. And again, you got to be careful, we have to add the x and the 4. And you also have to be careful and realize that you take in 4 times the quantity of x plus 4. And so we're going to have to distribute here. So you get 91 equals 4x plus 16. 4x is equal to 75. Divide by 4. And x ends up being 75 over 4. Or if you want to, 18.75 would be fine if you want to divide it out. Okay? The good news is if the segments cross outside the circle, the thought process stays the same. Okay? If you have a secant and a tangent that meet outside, then the thought process is the same. We're still going to take the outside piece times the whole. And then the weird part is with the tangent, the outside piece and the whole thing are exactly the same. So PQ times PR is going to equal PS times PS. So we're still doing outside piece times whole equals outside piece times whole. It's just that for the tangent, like I said, the outside piece and the whole end up being the same thing. So, quick example of this. Looking at segment lengths, no angles or arcs in this picture. And so that's the thought process we're going to use. The outside piece, which is 6, times the whole thing, which is 6 plus 4, which is 10. Make that better. Is equal to the outside piece, which is x, times the whole thing, which is x again. So just multiply by x again. So you get 60 equals x squared, square root, and x ends up being 2 square root of 15. Okay, and that's it. Now, try it. There are 3 problems here. Think about where's the segment crossing, where are the segments crossing. Find that window in your spinner and put this together. Stop the video, give it a shot, start it back up and see if you're right. All right, did you get this? Right, so the first one, the segments are crossing inside. So we're going to do piece times piece equals piece times piece. And so that's where that equation comes from. Number 2, the 2 segments are crossing outside the circle, so we're taking outside piece times whole, outside piece times whole, and you get that. And then number 3, same thing, the segments are crossing outside the circle, so we're taking outside piece times the whole, which is the same thing for that tangent, so you get x times x, and setting it equal to outside piece times the whole, which is 27. So 3 times 27, and you work that out from there. Okay? Hopefully that makes enough sense. If not, make sure you come find me and we'll go over it some more. Okay? Now, the last part here. If we ever want to take a circle and put it in the coordinate plane, and the reason why we do that is the same reason we do that for any other shape that we try to put in the coordinate plane. It gives us a frame of reference. It allows us to find some different measures a little bit easier. And using the distance formula and stuff like that. So if we do, then the second we put that circle into a coordinate plane, it's going to have an equation that describes it, that goes along with it. Okay? And so the question is, what does that equation look like and where does it come from? Okay? Well, there's a couple of different thought processes here. If x comma y is a point on the circle, right? Say this point right here. And the center of the circle is at the origin, 0, 0, right? So if this is x comma y, then to get to that point, you would have to come over so far. You'd have to come over x this way and then go straight up y this way, which would create a right triangle, which means that now if you wanted to find the radius of the circle, which goes from the center to that point, you could just use Pythagorean theorem. R squared equals x squared plus y squared. And so that would be the equation of a circle whose center is at the origin. But what happens if the center is not at the origin? And something like if the center was here and the radius was here, okay? Now, real quickly, need to understand, there are two things that distinguish one circle from another, and it's the center and the radius. If two circles have different centers, then they're not the same circle. If they have two different radii, then they're not the same circle. So what we need to differentiate one circle from another in the coordinate plane is the center and the radius. And if we have those two pieces, then we can write the equation of a circle. And I'm going to show you how. Okay? So now we're going to take a look at a situation where the circle's center is not at the radius. We still want to talk about a point being here at x comma y. Now, since we're using x comma y for the point on the circle, for the center we have to use different points, and so we usually call it h comma k. H and k are just arbitrary. There's no real rhyme or reason for why we do h and k. It's just someone started it a long time ago and we just kind of stuck with it. Okay? Now, so I have the center of this circle. I need the radius. The radius is defined as the distance from the center to a point on the circle. How do we find the distance from one point to another in the coordinate plane? That would be the distance formula. Okay? The distance formula here would look like, well, again, the distance from this point to this point is going to be the radius. So this distance is just going to tell us the radius. Well, the distance formula says subtract the x's, which is going to be x minus h, square that difference. Subtract the y's, square that difference, and take the square root. Now, we can clean this up a little bit if we square both sides of this equation. And when we do, we get r squared equals x minus h squared plus y minus k squared. And that is your standard form of the equation of a circle. And it's here. It's also on the outside of your spinner. Okay, so what do we know? Well, the x and the y are always reserved for any point on the circle, so we need to have the x and y in there because there are a bunch of different points on the circle. I need to be able to plug in a bunch of different points for x and y. So since we don't know what x and y are, we leave them there. H and k are your coordinates for the center, and because the distance formula says you have to subtract the x's and subtract the y's, notice that from the coordinate to placing it in the equation of a circle, the sign changes. You get this minus, right? So if h were 2, you get x minus 2. So if it were positive 2, then the equation would have you doing x minus 2. Where if the x was negative 2, you would get a minus a negative and therefore make this plus. So, in other words, the sign changes from the equation to the coordinate and from the coordinate to the equation. Okay? Same thing for the k. And we just saw that this side is equal to the radius squared. So to find the radius, we'd have to square root whatever number's in here. Okay? All right, let's try it out. Here is the equation of a circle. We want to graph it. So we need to know where the center is, and we need to know what the radius is. Well, the center is going to be, and again, you change the sign from the equation to the coordinate, or the coordinate to the equation. So since this is positive 3, I change that sign to a negative 3. And since this is negative 5, I change that sign to a positive 5. And that's the center. That's the coordinates for your center. So you go to negative 3, 5, which is right here. And then the radius is going to be the square root of that 16. Because remember that it's equal to the radius squared. The equation is equal to the radius squared. So the radius is equal to, here, 4. So if the radius is 4, I can count 4 grid lines in all directions. 1, 2, 3, 4, puts a point here. Up goes 1, 2, 3, 4, puts a point here. Left, 1, 2, 3, 4. Down, 1, 2, 3, 4. And draw your circle through those points, and you've graphed the circle. Okay? And that's it. We're done. Okay, you try it with this one. Try to find the center, the radius, graph it, start the video back up, and see if you did it correctly. Did you get this? The center is at 2, 5 because we changed the signs. We didn't pull out of the equation. And the radius is the square root of 9, so the radius is 3. Okay? So we go to 2, 5, place our center there, and then count 3 grid lines. Up, down, left, right, draw a circle. Okay? Now, we need to be able to write the equation. So go from the graph and write the equation. Again, the two things that we have to have the center and we have to have the radius. The center of this circle is given to us at -1, 3. So we could start by going x minus the -1 is x plus 1, y minus 3, and now we have to have the radius so that we can put in, so we can square that and put that into the equation. Again, the radius is defined as the distance from the center to any point on the circle. So, distance formula for those 2 points. So the radius is going to be equal to the square root of -1 plus 5 squared plus 3 minus 6 squared, which is 4 squared plus -3 squared, which is 16 plus 9, so the square root of 25, and so the radius is actually 5. When we put it into the equation, we've got to square that 5, so this is 5 squared, which is 25. And we're done. Okay? Some more writing the equation, but a little bit easier. Need to know where the center is. The center is right here, which is at 0, 2. The radius, we can go directly out and see that the radius is 2. Left, it's 2. Up, it's 2. Down, it's 2. So the radius must be 2. So when we put this into the equation, we get x minus 0 squared plus y minus 2 squared equals, square that 2, and you get 4. Now what you'll see is, since this is x minus 0 inside these parentheses, you'll see the 0 get dropped. And so it'll just be x squared plus y minus 2 squared equals 4. And then we're done. Okay? All right, you try. Write the equation given the information. And you should get that. Okay, change the signs. X minus 3, y minus 3. And then you square that 4 to get 16, and that's your radius squared. And that's the equation. Okay? All right, that's it. Homework's out in Canvas. Make sure you get to it by next time.